Okay, thank you very much for that kind introduction. And wow, it's just such a pleasure to be here today and be sharing this virtual stage with some truly talented engineers doing some really inspired work. And Lee, thank you for your leadership on this panel today. It's good to be with you. I'm going to get this going from the start here. So I go by Will, that's me. I'm a scientist and engineer at the Johns Hopkins University Applied Physics Lab and a lecturer at the Whiting School of Engineering at Johns Hopkins there. My background actually started in sleep research, and that's always been kind of my one true love. It's taken on various facets over time, passing through brain-computer interface and artificial intelligence, and a little bit of all of those components is in this work that I'd like to share with you today. Really the goal here, and here's the team at the bottom. This is our clinical associate at the School of Medicine at Hopkins, who first had this idea and brought this amazing data set to us. So much thanks to Naresh here and the team on support at APL. We have a simple goal. We want a system that can measure sleep signals, including brain activity, at home without expert training or needing expert technicians, that can be automatically interpreted by some trained model or AI. It might be in the cloud, it might not, and translate that into a meaningful representation of a person's sleep patterns. I think I like to think of like two major driving forces for this, or two bins you can think of. The first, which has really been revealed in its entirety during the COVID situation, is this rapid transition to telemedicine. So there's an obvious impetus to get diagnostics out into the field without requiring people to transit into a laboratory environment in the current situation, in the pandemic, of course. But there's also an inherent value in measuring sleep in the natural state. This is often my quantum mechanics joke. You come into the lab and your sleep is altered by being in a novel environment, so you've changed the outcome by measuring it, essentially. So by measuring the same signals in the home, you're going to get a better snapshot of that individual's sleep patterns, which will be, it'll facilitate diagnosis in a number of ways. And the other thing that I'm always thinking about is how much we've kind of subsumed control over our own personal health data, right? We count our steps, we count our minutes of exercise. Apple Watch does all of this for us, our Fitbits. And it's hard for me to imagine a world much longer where we're spending time counting steps and not also having interest in counting sheep, which, sleep is fundamental to virtually every aspect of health and well-being. So it's really valuable personal data to have for behavioral change and just monitoring. Just some background on the problem space we're working at. The traditional gold standard for measuring sleep is called polysomnography. Poly just because it's an aggregate of these electrical differential recordings around the eyes, the EOG, the EMG to detect muscle tone, and then typically a few electrodes over the scalp to detect brain activity. You come into a lab and a trained technician can spend 45 minutes measuring and carefully applying these in specific locations. This is the International 1020 system. You're looking at a top-down view of a head with the nose up there at the top. So, and there on the right is a very, very young version of me as a undergraduate intern at Brown University's Sleep and Chronobiology Lab, measuring a subject for a sleep study. They, by the way, run the best didactic summer internship for this kind of work. So if you're a young and ambitious engineer or scientist, I encourage you to check them out for internship opportunities. Okay, so you've got your sensors on in the lab. You're going to go to sleep in this novel foreign environment, and you're going to have somebody watching you. That's primarily for safety reasons. And after your night is over, you pack up your stuff, you go home, and that technician sits down for half an hour and pores over these signals 30 seconds at a time. 30 second, we call it an epoch in sleep. And I'll distinguish epoch. When I say it here, I mean a sleep epoch, a 30-second window of time, not the machine learning neural smithing epoch that we run into when we're training our neural networks for the savvy audience member out there. Okay, so you're looking at 30-second chunks of time and producing at the end of your experience this diagram of sleep. And one of the first things that pops out at this diagram here, this cartoon, is the cyclic pattern. The sleep is cyclical, and it cycles through these different sleep stages over the course of the night. And that contains a lot of useful information. So that's our first marker that we want a model to pay attention to those patterns, that sequence, the temporal sequence, because it's important and it tells you about the state that you're trying to identify. Now, briefly, you start out in light non-REM N1, and then deeper levels of sleep through non-REM stage 2, and then finally in N3, which is actually, it used to be 3 and 4, but now it's just N3. This is deep, deep, slow wave sleep. We'll talk about an interesting effect later with that. And then you pop back up into your rapid eye movement sleep, your dreaming sleep. All right, so we know that the sequence is important, and I also think it's really helpful to get a grok on what the features that we're looking at for our model. What are we trying to capture in addition to the sequence? What does the technician see that we would like our model to see? And so really it's quite nice. They have these very precise rules, and all of these features kind of pop out to the human eye. They're set up for perceptual detection. Alpha waves, for example, this kind of 10 hertz oscillation over the back of the head visual cortex disappears at sleep onset, and once you transition into the next stage, stage 2, you start to see these singular slow wave events called K-complexes, or sleep spindles, these little faster enveloped waveforms. And then by the time you get to N3, you have these big honking slow waves, the 2 to 4 hertz, that traverse the cortex, and the entire brain is basically just kind of shut down and pulsing at that frequency. Of course, the eye movements we need for determining REM sleep, and muscle tone also for REM. Muscle tone disappears so you don't act out your dreams, actually, and the eye movements are needed because the brain activity during REM sleep is indistinguishable from the brain activity during wake, which is really interesting to think about. So for this study, we had a little over 800 records to look at, and we're kind of in the middle, or mostly towards the end of the project. So one thing we did very early on was set aside 50% of the data as a holdout validation set, and we haven't laid eyes on that yet. We're wrapping up what we've done in the first 50%, so I'll be reporting results on something closer to 300 records today. And compared to polysomnography at the right, you see our sensor acquisition system, and the whole idea here is simplicity. This is something that it's not a dry contact electrode, so it won't slip away from where you put it on. It's easy for a subject without any training at all to just, clean their face, put this on in a mirror before bed, and they're good to go. So it's just a cluster of sensors right there on the front. And of course, it's capturing in each of these some amalgamation of eye movement activity. This is that ocular potential that you can detect principally here when the eye moves in its orbit on that gradient there. And it's also detecting a lot of frontal brain activity. And there's a mix, I think, in all of these channels. And of course, each of those sensors is looking at quite a large area of cortex. So spatial specificity starts to, doesn't buy you much anymore at this stage of the game, or for the signal features that we're looking at. And each sensor is detecting about 10 square centimeters of cortical real estate. So we've got cortical activity, we've got eye activity going into these hybrids kind of signals. And one of our goals eventually is to reduce the footprint even further, but this may be sufficient in its current design. One important difference, we have the sensors all clustered at the front. We don't use the traditional referencing, which usually sits behind the ears on a kind of isoelectric bony protrusion called the mastoid. And it's a great anchor point to reference your differential signals to, and without that, it has some interesting, I think, outcomes that we didn't anticipate. More on that later. And I'll skip by the details here. This is all in the paper, just if you're curious about how we reference the signals. Follow up on that in your own time, I think. All right, so earlier today, actually, David gave just such a really nice description of temporal sequence modeling in his gated recurrent units, which is, of course, a flavor of recurrent neural networks. And this is another flavor of the same principle. We mentioned right at the beginning that the sequence, the cycling of sleep, contains a lot of information. So we want the model to have that. And we also want to give it features. So what pops to a technician? What do we think that the model needs to be aware of? And these are these brainwave grapho elements that we looked at previously. And the idea here is to we have two modules in our system. We have a module that handles the feature extraction. Of course, we all know how good convolutional neural networks are at these kind of perceptual tasks, right? They're doing pretty much what our visual cortex is doing. And then feeding that information to this part of the model that keeps a larger eye on the temporal context. So it's actually considering 50 minutes of sleep, which is 100 of those epochs at a time. All right, now here's a really interesting point. For most of you who've done machine learning, I think you're working with MNIST, for example, or image classification. You're aiming for a really high, almost perfect classification accuracy, maybe something like 99%, and your algorithm does 99.1%, and that's a huge improvement. You publish a paper on it. That's well and good when you have ground truth, black and white labels, but an interesting problem with sleep is there is no black and white ground truth. We have these deterministic rules. When you see this, if this, and if that, and if not that, it is stage whatever. But those are interpreted by humans, subjective judgment, so there's discrepancy. And generally speaking, you try to aim in a clinical lab for 70 to 80% agreement between yourself in the past and your coworker on the left. Between the two of your scoring patterns. So really the labels themselves don't get much better than 85% at the high end in a really good clinical research laboratory. So that's kind of the high mark for where we want to aim. Okay, just very simply, we rapidly reach an asymptote, so there's not much point in extensively training this, which is nice because we gave it such a large corpus of data that seemed to be sufficient. And I'm just going to compare our results, which will be on the right, to this beautiful paper, Henri's work here from last year, as a benchmark. This confusion matrix actually quite nicely represents the true labels, quote unquote, versus his prediction, his algorithm. And that's using a very similar CNN RNN to what we're using here. And it would look virtually the same if I gave you expert rater 1 versus expert rater 2. They would make the same mistakes. They would see the off-axis N1, N2, N3 here. They would not be so good at distinguishing N1 because it's a transition state. And interestingly, in our sensor results, which are that forehead cluster instead of these traditional EEG plus EOG all over the head, remarkably similar results. 45 and 44, we get 87, 88% for N2, and comparable for wake and REM with some loss. But the thing that really jumped out to us was this drop in sensitivity to stage 3, which is curious because stage 3 is just so obvious to an expert. It's one of the easiest stages to recognize because it's all big, slow, high amplitude oscillations. And evidence number 2 that something was awry was when we go to this minimum set, just 2 differential channels from 4 sensors essentially. We lose sensitivity to N3 entirely. No, not at all. Thank you. I appreciate the time. Okay, yes. It actually looks like we're right on track. Okay, yeah, so After we started to think about this, the interesting phenomenon, without that reference, that mastoid reference or something isoelectric elsewhere, you're canceling out essentially the slow wave. Slow waves are spatially widespread, and if you have a slow wave on the left front of your forehead, you have a slow wave on the right front of your forehead. And if you have them in both channels of a differential signal, you're just subtracting them out. So this system loses sensitivity to this deep slow wave sleep because of that referencing. And sure enough, if you look at the signals, you see greatly diminished amplitude in the slow wave sleep. So an obvious improvement would be to just stick another sensor maybe behind the ear on the mastoid if it will stick for the entire night. Something worth exploring. So this is really just an end-to-end system. It's a great example, I think, of just good, solid systems engineering. Each of the individual components isn't a revolution in and of itself, but it is the right set of tools for the job that together, I think, become more than the sum of their parts. And there is such an opportunity in this space right now. Everybody is rushing to have the latest, greatest device or wearable and to track your own data. And now we have this amazing clinical opportunity as telemedicine becomes the status quo. So there's going to be a lot of activity in this field, and we need people like you, those who are attending this conference, and if you're an undergrad or a grad student, I'm almost jealous. I wish I could go back in time. There is no better or no more exciting time to be an engineering student in medicine and biology than right now. So I'm very excited to see what you will all do. And if you're interested in any of this work, please do contact me. Some of the future directions we're exploring include real-time sleep pattern classification with neurostimulation. And the point of the graph on the left is not to spend time on the details, but just to show how many different things you can do stimulating the brain during sleep with real-time systems. You can manipulate memory or quality of sleep or duration, so some really interesting future paths. And it even has some kind of unexpected interesting offshoots, like some recent work we've done training neural networks to mimic sleep states the way our brains process information during sleep. And we've seen performance boosts that we would like to port over to our brand new Boston Dynamics Spot Dog. So I think we're right past time. We have a couple minutes maybe for questions. There's some contact information. And again, it's been a privilege to share the stage with you all. Thank you so much for your attention. That's a great question, and a keen eye, astute observation. N1 it's kind of a transition state. You don't spend a lot of time in N1. The reason you have an N1 is because you're either woken up and you're going back into a deeper stage of sleep and you have to kind of pass through this hierarchy, or you are waking up and coming out of a deep stage to a lighter stage, and you might pop into N1 as you kind of roll over and move around. So because of that, it tends to be buttressed by all kinds of different stages, and those boundaries between them can get murky, and different experts will have a different opinion essentially on where those boundaries lie. N1 is particularly susceptible to that subjective component. No worries. Yep, they have all my contact information. I would be delighted to hear from anyone. Thank you.